Welcome to Dr. Jed's continuing calculus series. This is section 4.9 from Rogowski, which is antiderivatives. You'll notice we skipped 4.8. It's very interesting, and if you want, you can feel free to read it, but it's not part of the syllabus, so we're not covering it. 4.9 is actually very complicated and a little bit messy. However, conceptually, it's very simple. We're going to talk about what the definition of an antiderivative is, list out the rules, talk briefly about what an initial value problem is, and then give some examples. It's actually going to be fairly simple. Hopefully. What is the definition? Well, if f is a function, remember how we always talk about differentiable functions? Well, we're not so concerned anymore because it's just some kind of function that, well, it has an antiderivative. An antiderivative is some other function, f. Now we pause for a second. Notice, this is little f, this is big F. If you like to think of them as the same thing, you're going to be in trouble here because they are not. Big F is the antiderivative. What does that mean? It means its derivative is little f. So for example, if we had x cubed, its derivative would be 3x squared. So the antiderivative of 3x squared would be x cubed. Except we'll get to it. X cubed is one of them. How do we notate it? Well, this is our notation for an antiderivative. It's the set of all antiderivatives, actually. And how do these antiderivatives look different from each other? Let's take a look. If we have one antiderivative, we can find any other one we want by adding a number to it. Why is that? It's because, well, in that example, 3x squared was our function, right? Well, an antiderivative would be x cubed. Because the derivative of this is 3x squared. But so would, so this is little f, this is big F. But so would x cubed plus 2, because what's the derivative of that? 3x squared plus 0. The constant goes away in the derivative. So we can add any constant we want. Here's another example. The antiderivative of cosine of x dx is the sine of x plus c. Why? Because the derivative of the sine of x plus c is that cosine. Think about it for a second. Hopefully this makes sense. Here's the function. We take its derivative and it goes in here. Or more precisely, here's our function. We take its antiderivative and it comes out here. Notice this piece. This tells us it's an antiderivative, but so does this. They're kind of bookend pieces. And this is an important piece. Right now it may not seem like much because it's always dx. But later it could be a different thing, and it will be critical in the next chapter that you keep track of what this is. Anyway, there are rules for this. Remember, we had rules for derivatives. If we started here and came this way, how do we know this one? Because we know the derivative of a sine. Likewise, we know the derivative of the cosine, of x squared, of x to the fifth, of e to the x, and all sorts of things. Using those rules, we can find rules for antiderivatives. Start with powers. The antiderivative of x to the n, well, normally with derivatives, you subtract one power and bring something down, right? Well, here, we're going to add one power, and instead of bringing the number down, we're dividing by it. This works great unless n is minus 1, because then you've got dividing by 0. Dividing by 0 is not fun. So the special case, when n is minus 1, is the natural log. And this should look familiar, because the derivative of the natural log is 1 over x. The only thing different here is the absolute value is there. So it's a little bit different in that sense, but it's an extension of that idea. What else do we know? Exponentials. Well, the derivative of e to the x is e to the x. The derivative of the derivative of e kx plus b would be e to the kx plus b times the derivative of that, which is k. So the antiderivative takes that into account. The antiderivative of e to the kx plus b is e to the kx plus b divided by k, and then plus an arbitrary constant. Plus 7, plus 2, plus 19, plus 0, doesn't matter. Any of those would work. Two more. One for the sine, one for the cosine. We're trying to get fancy here. Not just the sine of x, not just the cosine of x, but we're putting kx plus b in there. And again, it comes out here and here. The 1 over k, because when you take the derivative of this, it's the chain rule. These are rules. They're the rules for derivatives written backwards. That's all. They may look messy, a little bit confusing, but you've actually learned these rules before going the other way. There are a lot more rules. There's a chain rule, there's a product rule, there's a quotient rule, But, and in fact, like there's rules for tangent and secant and hyperbolic secant. Inverse sine, we're not going to dwell on those right now. We're just doing these few because these are easy to go backwards. Now, one other little bit in this section, initial value problems. What is an initial value problem? It's simply a differential equation, we've studied those, with an initial condition added on. The initial condition will give us a specific answer rather than a general solution. We'll do one of those. Let's move over here to that initial value problem. Solve this initial value problem, this differential equation with a condition. I want to know, well, the derivative is 2x. What's the function? Hopefully you know enough about derivatives to say y equals x squared. But that's not right. We know antiderivatives now, hopefully enough, to recognize there's another piece missing. Any number could go there. 2, 15, 93, because the derivative of x squared plus 93 would be 2x plus, that goes away, 0. We also know that y of 0 is 4. This is where the initial value comes in. Y of 0 means we plug 0 in for x. And it tells us that c is 4. So finally, our answer is y equals x squared plus 4. That's what the initial value problem solution is. That specific function. Sometimes more complicated differential equations can have constants going in all sorts of places. For now, that's probably what you'll see. Now, a little practice on antiderivatives in general. Using those rules we just learned, the antiderivative of e to the 2x plus x cubed, well, derivatives, when I add, I just take the derivative of each piece and add them together. Antiderivatives are the same. So the antiderivative of e to the 2x is 1/2 e to the 2x. The derivative of x cubed is x to the 4th over 4. A prettier way to write that is 1/4 x to the 4th. But there's one more thing you need for the general antiderivative. You need a plus c. Hopefully that one made sense. Now come a couple that are a little trickier. This is x to the 1/2, right? We're taking the antiderivative of x to the 1/2. When I take the derivative, I subtract 1 from that power. When I anti-differentiate, I add 1 to that power. So I get x to the 3/2. Now, I could then divide it by 3/2. Divide by 3/2, divide by a fraction is the same as multiplying by the reciprocal fraction. The next piece here is the pi to the x. Pi to the x, we don't have a rule for pi to the x. We only have a rule for e to the x. So I'm going to change this. I'm going to write this as, well, pi is e to the natural log of pi to the x, which is to say e to the natural log of pi times x. That fits the kx plus b, where b is 0. So the antiderivative of this will be 1 over the natural log of pi times pi to the x. And then we don't want to forget the plus c. Taking these rules is a little bit tricky. The concept is hopefully sensible, at least in abstract. We're just going backwards from derivatives. But as you can see, the formulas you learned going backwards are a little bit trickier, and they may be a little bit confusing. Take your time, practice, and you'll get it. Until next time, this is Dr. Jed.